All right, very good morning to all of you. Last session we were discussing MOSFET, power MOSFET, and then the turn on and turn off characteristics of the power MOSFET. The power MOSFET had stray capacitances across gate source that was denoted as CGS, and then there was a capacitance between the drain and gate drain capacitance CGD, whereas drain to source the capacitance is going to be negligible. Once the MOSFET is going to be turned on, completely turned on, the MOSFET will enter into the ohmic region where the VI characteristics saturation region is named as ohmic region in case of a power MOSFET. And we had the cutoff and the active region as usual. So this was the point that we had discussed in the previous session. You need to remember, I am recollecting, you need to remember that MOSFET is a voltage controlled majority carrier device. Therefore, MOSFET has the highest switching frequency among all the power devices. So if you, that is the key term to identify power MOSFET. If you come across this term, highest switching frequency, highest operating frequency, it is a power MOSFET. No other device comes nearer to that. Okay, because MOSFET can operate at megahertz switching frequency, whereas other devices, they lie in the kilohertz range. So that's about power MOSFET. In this session, we will take up the last of the power devices, which is IGBT, insulated gate bipolar transistor. So that will be the agenda for this session. It is quite simple because IGBT is a combination of power BJT and a power MOSFET. Therefore, it is quite easier to understand. Fine. So today's discussion will be on insulated IG gate bipolar transistor. IGBTs. Fine. Now there are other names for IGBTs as well. People call this as COMFET, people call this as IGTs, insulated gate transistor. That is another name that is commonly used. So the jury is still out, but IGBT has become quite a popular term. Now you need to remember that IGBT combines the advantage of, this is again another key term to identify the device. It is actually combining something like best of both worlds, that is IGBT, combines the advantages of BJT and power MOSFET. Power BJT and power MOSFET, so I will write it as BJT and MOSFET, that should be fine. We'll write BJT has got the lower on-state drop. In fact, I had mentioned that the MOSFET will have a higher on-state resistance, on-state ohmic resistance. And first session I told when I introduced MOSFET, I had mentioned that there are practical devices with low RDS on, low values of drain source resistance as well. So BJT has a lower on-state resistance, or I'll just put this as on-state voltage drop, on-state voltage drop, whereas I will complete this and then pass on to MOSFET. On-state voltage drop. Whereas if you take MOSFET, MOSFET has got the highest switching frequency, operating frequency. So that is the main advantage of a power MOSFET. There are drawbacks. If you take BJT, it has got low switching frequency, whereas if you take a MOSFET, it has got high on-state voltage drop, high on-state resistance, consequent voltage drop. So IGBT is going to combine the best of both worlds. Fine, that is the IGBT. Now, if you look into the structure of IGBT, this is the physical structure of IGBT, wherein there is the addition of this P plus layer. This is the difference between the power MOSFET and an IGBT. Construction wise, there is a P plus injecting layer. This is called as a P plus injecting layer. And then the other layers, N plus layer, N minus drift layer, they take N plus layer is called as the buffer layer. I do not know if it's mentioned. Yeah, it is mentioned here. Good. So N plus layer is called as the buffer layer, whereas N minus layer is obviously the drain drift region. And there is the P type body layer, which has got moderate doping level, 10 power minus 16 particles per cubic centimeter, and obviously the n plus source. Now, terminal wise also, there are few textbooks which name the terminals as collector and emitter. So drain will be equivalent to a collector, whereas source is termed as a emitter. So again, the jury is still out. If you look into the terminals, or if somebody wants you to name the terminals, people use gate emitter collector, or they use gate drain source, similar to a MOSFET. Both things are actually acceptable. That's what people tell. People that's how people understand. Fine. Now, gate drain source. So, okay, collector and emitter. Now, the structural difference is the presence of a P plus injecting layer. That is a structural difference. This structural difference is going to cause lower on-state voltage drop, and it will not be as high as MOSFET, the switching frequency, but it will be moderate. It will be in hundreds of kilohertz, 100 kilohertz, 150 kilohertz. Yes, an IGBT can quite easily operate with reasonably lower on-state voltage drop. It will be slightly more than a BJT, but definitely less than a MOSFET. That is the best of both worlds, combination of best of both worlds. Now, I will draw the symbol of an IGBT because it is a new device, and then I will mark the terminals. IV characteristics and switching characteristics, they are exactly similar to that of a MOSFET. So I'll draw the IV characteristics. Switching characteristics, turn on and turn off transient, exactly similar to that of a MOSFET, because its behavior is again similar to that of a MOSFET. So you don't need to worry. Now, before I draw the, of course, symbol is quite simple, no? Therefore, I will complete that. I'll draw the symbol first. See, it is insulated gate bipolar transistor. So transistor will have collector and emitter terminals. This is collector, and obviously this is the emitter terminal. But then you need to understand that gate is insulated. Therefore, have a space, allow some gap between the collector and emitter layer, and this forms the N-channel IGBT, gate, collector, and emitter. This is one symbol. This is more practically adopted. Again, there will be a structure which has got antibody diode as well, a parallel antibody diode. Some IGBTs come with this. Some IGBTs make sure that this antibody diode is, the effect of that antibody diode rather is negligible. So you do have two structures. You need to refer to the data sheet for confirmation. I will leave it there. Right. Now, the antibody diode gets into picture because of the effect of MOSFET, and the effect of transistor is seen over here. Fine. Then understanding the operation is going to be easy, and you will find that there is a parasitic SCR. There are three junctions, J1, J2, and J3, or rather there are PNPN layers, P plus, N, P, and N plus. So you have a 4-layer PNPN structure that forms a parasitic SCR. I will write this as parasitic SCR. Now this parasitic SCR, which is inside the IGBT, within the structure of IGBT, should not be inadvertently turned on. If you turn it on, then IGBT gets into latch. So you can also understand this IGBT or call this IGBT as a latch-up device. Of course, SCR is also a latch-up device. What is called as latching up? Once you get inside a room and then you lock, people from outside, they can't open up. So that is called as a latch up. Once you latch, that is called as latching. Once you lock, it's not lock, it's actually latch. So IGBT, you can understand this to be a latch up device as well. Latch up device is mainly due to the parasitic SCR. Due to the parasitic SCR. And there are methods to avoid latch up. For instance, instead of having, one minute, I'll scroll up. Yeah, instead of having this P layer spread out laterally, this P section is going to be divided into two. One towards the left of the source, one towards the left of the source. So if you have a vertical division, people adopt that structure. Vertically, it is going to be divided. And this p type will be divided between this and this. That is the left of that division and right of the source terminal. Our p type layer is going to be spread out rather than having one full layer spreading throughout the device laterally. They split that into two. That is going to avoid latch up. Structurally, there are modifications which avoid latch up. That is way beyond the scope of your content. You understand that IGBT has got a parasitic SCR. There will be latch up that is occurring inside the IGBT. That latch up has to be avoided. That is enough. Okay, and fourth point is again a deeper point. If you know that the structural modification of distributing the P layer is going to avoid the latch up in IGBT, that is more than enough. All right, next comes the VI characteristics of an IGBT. So that is again going to be very similar to that of a power MOSFET. Steady state VI characteristics. Now, the collector current or the drain current. I will use collector current, but Nedmohan uses drain current. And the terminals are going to be, I will again use collector emitter, whereas Nedmohan uses drain source. I am telling you the difference as well. VCE, IC versus VCE for various values of VGE, gate emitter. Here I think I haven't marked the emitter. I will name the emitter terminal here. This is the emitter terminal, gate collector emitter. Fine. Now the characteristics are like this. It will be like this. If you start somewhere, because of the inherent drop, there will be a voltage drop VCE on, and then it starts. Again, you will have this threshold, etc. There will be a gate source threshold voltage because it is similar to that of a MOSFET. I will name this as VGS threshold. It is exactly similar, and there will be one VGS maximum. Not VGS, I'm sorry, I will correct, it is VGE. Gate emitter, because I have plotted with respect to emitter. So gate emitter maximum value, gate emitter threshold value. And in between you will have various values of gate and emitter. Right. So this is the VI characteristics. Obviously, this one, this voltage. So if you draw a straight line here, it will definitely be a straight line. So this will be VCE on, the on state voltage drop. VCE on of the IGBT. That's all. These are the VI characteristics of the IGBT. And then switching characteristics, exactly similar to that of a power MOSFET, both turn on and turn off. Absolutely no difference at all. Only difference is there will be a minor difference in the fall time for during turn on process, and IGBT takes a lot more time to move from the active region to the ohmic region. I repeat, during turn on, the IGBT takes a lot more time compared to a MOSFET to move from active region to ohmic region. Therefore, the fall in voltage, fall in VCE will be a little bit gradual. Whereas in a MOSFET, if you can recollect, it will be drastic. The fall in voltage for TEF V1, TEF V2 fall times. In an IGBT, those two fall times, fall intervals will be longer. That's all. That is the only difference. Principle wise, it is same. Capacitance effect causes the current to rise gradually. Threshold voltage should be set up. Gate capacitance should be fully charged. Only then the conduction, everything is going to be exactly same. Okay. So I will just indicate that, and then I will move on. With that, actually, the list of power devices, set of power devices are over. Probably I will tell about GaN, gallium nitride and silicon carbide devices. With that, I will wind up for today. Now, the switching transients, I will just indicate here and I will leave that to you, the reference part. Switching characteristics are exactly similar to that of a MOSFET. Or exactly similar to that of a MOSFET. Only changes would be there will be the fall time intervals will be longer. Now, longer means the switching frequency of IGBT will come down because time is more, so frequency is going to come down. It will take a longer time for turning on and turning off. That's all. So, switching characteristics again you can refer to Nidmohan. I forgot to write that this image is taken from Nidmohan. So this image is reference Nidmohan textbook chapter 25. So again same chapter 25. The switching characteristics, VA characteristics, explanation to them, they are going to be available. So you can take them and then you can start referring. If you you can recollect the VA characteristics of a BJT, base current, we would have plotted the IC, collector current, versus again the same collector emitter voltage for various values of base current, IB, in a power BJT. So BJT is a current controlled device. Power MOSFET, it would have been VGS, gate source. Power MOSFET, it would have been VGS. Control variable is voltage. Now, coming to IGBT, you can follow the same logic. It is gate emitter voltage. So IGBT is voltage controlled IGBT. Voltage controlled device. BJT is a minority carrier device, whereas MOSFET is a majority carrier device. Because IGBT combines the best of both worlds, the jury is still out whether it is a minority or majority, and you can't tell both. Now, the advanced power devices, of course, this is going to be more important for you people and younger generation. Old people like me, probably, yes, I am introduced to them, but then it's not cheap. I haven't used one myself so far. So be attentive for the next 5-10 minutes, that's all. So you have what are called as silicon carbide, SiC, silicon carbide. Silicon carbide, this is one, and then gallium nitride, GaN. People call this as GaN, gallium nitride. These two things are called as band gap energy devices. Band gap energy devices, I'll just stop. Energy I will stop, and I mean I'll discard, and then I'll write band gap devices. I hope you can recollect the Niels Bohr atom model, and then you have what is called as valence band, conduction band, etc. And then you have this gap between two bands. That is where the semiconductor is going to be located, the energy level, and then we need to move the electrons cross over that band gap. So silicon carbide and gallium nitride, that compound devices made of this compound, they are called as band gap devices. The best advantage, the main feature of these two devices are generally band gap devices. There are other band gap devices as well. The main advantage of band gap devices are one main advantage is they have got a very good thermal They are thermally very stable, very good. I will write they are thermally very stable. That is going to be meaningful. Thermally stable. Now, what does this mean? Thermally stable. It means they don't suffer from thermal runaway problem so easily. They can withstand or they can operate at high junction temperature, withstand high junction temperatures without causing thermal runaway problem. That is the meaning of being thermally stable. Thermal runaway doesn't occur so easily. In fact, SiC, silicon carbide device, can be operated till 1000 degrees centigrade. And in a power converter, you will never reach 1000 degrees centigrade. Till that, it will be very, very, very stable. Whereas if you take IGBTs, if you take SCRs, if you take what is that power MOSFETs, 250, 300 degrees C, that is the maximum operating junction temperature. You can take data sheet and then you can find out. If you go beyond 65 degree or 100 degrees C, then for each increment in 1 degree Celsius, the current is going to be exceedingly high. Thermal runaway sets in very, very quickly in the semiconductor devices. Whereas in band gap devices, because of the energy band and the gap between two bands, high energy level, they are going to be thermally stable. Right? Therefore, these two devices are preferred for very high power rating applications. Very high power applications. Let's say if you want to operate in megawatt range, then you prefer SiC devices. Whereas if you want to operate in 100 watts, 200 watts, 1 kilowatt, 5 kilowatt, no, SiC and GaN, their cost is going to be prohibitively high. So far, there are commercially available SiC and gallium nitride devices. They are available. But if you compare the cost versus the power rating, only at megawatt scale, it becomes meaningful, which means I can't probably out of my own interest, I can buy a silicon carbide device, I can use it in a boost converter, or you can use it in buck converter or AC/DC rectifier, and then I can show it in lab, telling that this is a SiC based rectifier. But you will never be able to feel the advantage of using an SiC device unless and until you operate at megawatt scale, because that is where the junction temperature is going to be high, and that is where SiC is going to score. All right, so operating SiC at low power levels, you won't be able to feel the difference. You will never be able to see the difference, feel the difference. So that is one, these are few points. There is one drawback, especially with regards to gallium nitride device. So the drawback is going to be the gate triggering is a bit complicated, very, very sensitive device, especially the gallium nitride device. Gate triggering, bit complicated. Triggering 1 or no, TRIGG. Gate triggering is slightly sensitive and complicated. But to avoid that complexity, GaN devices come along with gate circuitry. They are embedded. The gate triggering part is embedded along with the gallium nitride device. It is not like this is where 1 minute I will complete this. Sensitive and complicated. So normally what we do is we will have the power section separately. In fact, in lab also I have demonstrated. We will have the triggering part separate and we will have the power circuit part separate. Finally, we will integrate them. We will integrate the gate with the power circuit through patch cards. That is what we do in lab. That is what we do in power electronics. Whereas gallium nitride, they are embedded. The gate triggering part comes within the device. Okay, because of this complexity. So that's about silicon carbide and gallium nitride, GaN devices. I'm not getting on with the structure of SiC, the operating principle and other things, because again, beyond the scope of the syllabus. But anyway, you should know these things. That is why I'm saying these things. Not outdated things like what is the on-state voltage drop of a diode? And you will write 0.7. If it is correct, I will put 1 mark. No, that is wrong. Wrong meaning practically no, it is not 0.7 always. I have used a power device, power diode with a voltage drop of 0.45. It can withstand 60 volt, it can carry 10 amperes. It carried, practically it carried 5 amperes. All right, so please be aware of these things. Please understand that textbook stuff is something, practically it is a bit advanced, and that is my role. I feel that is my role. I should tell you what is the advanced thing in place, but I should tell you first what is available in textbook. I think I am doing that blending job reasonably okay.